Hi, everyone, and welcome back. It's Kira Garfolo here with Greenville Tech's Math 109. Today, we're going to skip ahead and talk about Chapter 7, which is very much related to what we've been doing already. In 7.1, we're going to talk about systems of linear equations in three variables. So remember from an earlier section, section 2.3 to be specific, that a system of equations is simply a collection of linear equations that must all be true. So if we find a solution to this system, then we have found a combination of variable values that makes all of our equations true. Remember that we were solving earlier for x and y in those systems of two equations. Today, we're going to talk about in three variables, and really what we apply today can extend beyond three variables, but our course limits it to three. Generally speaking, we're going to be working with x and y and z. Although remember, we could really have, t, u, and v, or w, x, and y. Really, it can be any three variables, but most commonly, I'm going to use x, y, and z. Now let's talk about an example scenario that's going to follow us through this section, as well as we'll come back to it in the next section when we talk about that lecture as well. So in this scenario, we have a construction company who makes three models of storage sheds. They have Model A, Model B, and Model C. They also have three types of employees. They have people who do the framing, people who do the roofing, and people who finish off the interior. In this table, we can see how many hours of each type of labor each model of shed takes. So in Model A, it requires 20 hours of framing, 10 hours of roofing, and 30 hours of finishing. For B, we have 30 hours of framing, 20 hours of roofing, and 30 hours of finishing again. And for C, we have 40 hours of framing, 30 hours of roofing, and 50 hours of finishing. Now, to complicate matters, each month they have limited resources, right? So they only have 560 hours of framing labor, 380 hours of roofing labor, and 680 hours of interior finish labor. We want to know how many of each model they should make in order to use all of their available labor. So we want to keep all of their employees busy. How can we do that to find the intersection? So we're going to set up a system of equations. Let x be the number of Model A that we create, let y be the number of Model B that we create, and let z be the number of Model C that we create. If we write this into a system of equations, we'll get the following system. 20x plus 30y plus 40z equals 560. Now notice here, make sure that you go back to the table and look and make sure that you can replicate these equations, okay? 20x plus 30y plus 40z goes down that column for A because we're talking about framing here. So A will take 20 hours, B will take 30 hours, and C will take 40 hours to be a total of 560 framing hours. Similarly, 10, 20, and 30 for roofing, and 30, 30, and 50 for interior finishing. If we find the solution here, we'll find the sweet spot where all of the employees are busy, nobody's sitting around waiting on somebody else to finish. If we remember what we did in the earlier section, we talked about substitution and elimination. And while we're kind of going to be using the same concept here, we're going to have to use a slightly different approach when we're dealing with three. It's very difficult. These could be solved graphically if you can graph in 3 dimensions and you can envision things in 3 dimensions, but it's actually a lot easier and a lot simpler to use some other methods that we're going to learn about today. So these methods are going to rely on something called elementary operations. So given that system of linear equations, we can perform any combination of these operations to get what is called an equivalent system. Basically, it's just a system. It has different numbers, but the solutions will remain identical. So in any system, we can swap two equations. So where the first one was, we can move down to the second and just swap places. We can also multiply an equation by a non-zero coefficient. So that first row we can multiply by 3. As long as we do it to all of the elements in that first row, we're fine. Now here's where it gets kind of tricky until you get a little bit of practice. We can also multiply an equation by a non-zero number like we just saw, and we can add it to another equation, replacing that second equation with the result that we get. Now these rules will hold for systems in 2 variables, 3 variables, and beyond. So our example that we're going to look at is only in 2 variables for simplicity's sake. So let's consider these equivalent systems. Our original system here is x plus y equals 7, and 2x minus y equals 8. Our first equivalent system is 2x minus y equals 8 and x plus y equals 7. Notice these are the exact same equations. We've just flip-flopped which one comes first. So that's totally valid. Now in the next system that we see 3x plus 3y equals 21 and 2x minus y equals 8. Here we see that this last equation stayed the same, but the first one is simply 3 times that first equation up here. Totally valid, won't change our results. And lastly, we have this system. X plus y equals 7, so the first equation didn't change. But the second row becomes 3x plus 0y equals 15. So what we've done here is we've added the first plus the second, and that's where we've replaced. So if x plus 2x is 3x, so it's going to replace the second one. Y plus minus y is going to be 0y, so it's going to replace this second one. And 7 plus 8 is 15, which is going to replace this second one. All 4 of these systems, 1, 2, 3, 4, are equivalent systems. And if we solved any of them, we'd get the exact same solution. Now we can also put our systems into something called row echelon form. And in row echelon form, all we're doing is writing our systems in a particular format to meet the following criteria. So each equation has to start with a different variable. So our first one will start with x, our second one will start with y, and our third one will start with z. Now that means that in the x, we can still have y and z, but in the next one, x has to be 0, and all that we're left with is y and z. And in the last one, all we're going to be left with is z. The first coefficient in each equation also must be 1. We are going to use elementary operations that we just saw, like swapping and multiplying and adding and multiplying and replacing. We're going to use those row operations, those elementary operations, to get into this form. The general form that you're going to look for when you're looking for row echelon form is this. We're going to have x plus some number times y plus some number times b equals d. Notice the x doesn't have a coefficient because it has to start with 1. So x is the same as 1x. Here we have y plus zz equals e. Again, it would be 0x here, 1y here. And down here, z equals f. So we'd have 0 for a coefficient for x, 0 for a coefficient for y, and 1 for a coefficient for z. Now notice here that this is the perk of row echelon form. Z equals f is at this bottom. So we know the value of z right away, which allows us to do something called back substitution. If we start at the bottom, we're going to see the value of our third variable. In most cases, that's going to be z. We're simply going to work backwards up with substitution and solve for each of the variables that we're missing. So let's apply this to our earlier example with the sheds. We can show that our earlier system can be transformed into row echelon form using those elementary row operations to get this form of an equivalent system. We're left with x plus 1.5y plus 2z equals 28, y plus 2z equals 20, and z equals 7. So automatically we know that z equals 7. Remember, the Z is the number of type C, model C, that we should build. So we should build 7 model Cs. We already know that from this form. Now we can work backwards and plug Z equals 7 up here into this one to solve for Y. So we know Z equals 7. And now if we plug 7 into this second one up, we get Y plus 2 times 7 equals 20, which tells us that Y has to be 6. So now we know that Y equals 6 and Z equals 7. Now we're going to use that top equation using the values that we already know for Y and Z so that we can solve for X. So we're left with X plus 1.5 times 6 plus 2 times 7 equals 28, which simplifies to be X plus 9 plus 14 equals 28, which simplifies to tell us X equals 5. I highly encourage you to pause this video and make sure that you can practice this, back substituting from Z equals 7 all the way up to solve for Y and then to solve for X. At the end of this, we're left with X equals 5, Y equals 6, and Z equals 7. Now remember that X is the number of model A's that we should build. Y is the model B's, and Z is the model C's. So we know that we should build 5 model A's, 6 model B's, and 7 model C's to maximize our labor. Again, I encourage you to take a few moments and make sure that you can replicate this, especially once you're given that row echelon form above. Now, row echelon form can tell us some other very valuable information, especially looking at that last row where it's solving for Z. If we see that Z equals F, where F is some number, then there is a unique solution, and we can use back substitution to solve. That's what we just saw in our example, where Z equals 7. We say, okay, well, Z is 7, and we're going to plug 7 into the previous one to solve for Y, and then we'll plug that Y and Z into the first one to solve for X. That's going to be in most of our cases. Sometimes, though, if we look at the last row, we're going to be left with 0 equals 0. And in this case, we have infinitely many solutions, which if you remember from 2.3, this is called a dependent system. So we ended up with a always true statement called a tautology. It's always true. 0 is always going to be equal to 0. And so we know that there are infinitely many solutions. Now, sometimes we're going to get the opposite of that. We're going to be left with 0 equals 1, or 0 equals 7, or 0 equals 103. Some 0 equals some non-zero number that isn't ever going to be true. 0 can only be equal to 0. In this case, there is no solution, and we're left with, as you recall, what is called an inconsistent system. So simply looking at the last row of your REF system can certainly tell you a lot about that system as far as whether it has a solution or infinitely many solutions or no solution at all. So in conclusion, hold off on doing the homework for this section until you have listened to 7.2 or at least read 7.2. We're going to discuss how to easily put something into row echelon form without having to do too much by hand at all, right? We have our calculators, we want to know how to use them. So you're welcome to do these operations by hand and to sort it out. It's a little bit like a puzzle, but we're going to discuss how to easily get these solutions in our calculator in 7.2. Just as a note, be careful while you're Googling this. I know that a lot of people like to Google for help, additional help with homework, things like that. You are in an area of algebra that is its own graduate level courses. I took an entire course at undergraduate level, and then I took another one and applied to statistics. So there are countless ways to apply this in upper level mathematics. For that reason, just be careful when you look on Google, okay? If you see something and it makes sense to you, great, go with it. But you may get in over your head and find some very advanced stuff that is not at all meant for this class. So just know that that advanced stuff is out there and that you are in no way responsible for anything that we see beyond what we are working on in class and in homework. So be sure to practice. This is an area that gets a little tricky for some people Again, 7.2 should help clarify it as far as how you're going to do it on a test or on your homework. Just know that no test questions are going to be any more in depth than what you're already going to have seen on your testing quizzes. Remember that there are so many reference notes for you available online. There's the departmental reference stuff. There are publisher references. There are other links everywhere throughout our Blackboard shell, so make sure you use that. Remember that I'm also available for my office hours and that the Math Center offers free tutoring in person and virtual at any time. You just need to go online and make an appointment. You can do drop-in for in-person tutoring, but it's not guaranteed that they'll be available, although I've usually not had any students have any issues. Thanks for tuning in. I hope to see you soon for section 7.2, where we'll continue to cover systems and learn how to use our calculators to do it for us. Have a great day.